Welcome back. We left off thinking about this question: is the Milky Way at the center of the universe? And if you didn't catch the setup to this video, you should watch the end of the last video where we talked about that question and drew a little diagram which showed why you might believe that the Milky Way is at the center of the universe, because all of the galaxies, no matter what direction they're in, seem to be moving directly away from us. So let's answer the question: are we in fact the center of the universe? It would be nice to think that, but every time in the past that we've thought that, we've turned out to be wrong. The Greeks thought that the Earth was the center of the universe and everything revolved around the Earth. We thought we were in the center of the galaxy for a time. All of those things turned out to be not true. So it would be kind of surprising if we were in fact the middle of the center of the universe. That would be unusual. Let's see why that isn't the case. I've got two pictures here. Here's one of them. It is a overhead transparency where I have drawn in a bunch of galaxies. I've painted one of them green and one of them red, and pink, and blue, and a whole bunch of other little galaxies here in the meantime. And if I've taken the same picture, and I just hit the enlarge button on the copier by 10%. That's all the difference between these two pictures is one of them has been enlarged by 10%. And the cool thing is you can reproduce the Hubble law with this thing. Watch this. If I line up the central galaxy, there it is. Get better lined up. There, look at that. That's better. You can see in this enlarged version of the universe from one to the other, you can see the Hubble law right here. So here we are in the center of this diagram, and you can see here's a galaxy and it's moving directly away from us, and here's a galaxy and it's moving directly away from us, and here's a galaxy that's moving directly away from us. All of these galaxies, you can see the two dots are the motions at one time and then another time when the universe has been enlarged by a factor of 10%. Not only that, you see the Hubble law. The further away a galaxy is from us, the faster away it's moving from us. Well, that's cool, but clearly we're special because we're here at the center, right? Wrong. What if I line up this blue galaxy instead of our galaxy? Well, look what happens. From the blue galaxy's vantage point, also it looks like the Hubble law is a thing. All galaxies are moving away from the blue galaxy, and the further away you get from that blue galaxy, including us, the faster that galaxy is moving away from that blue galaxy. Everybody sees the Hubble law. It isn't that galaxies are hurtling through space at near or faster than the speed of light velocities. It is that space itself is expanding. Look, I've lined up the red one. The red one sees this, the red around here sees the Hubble law. Everybody, no matter where you are in the universe, sees the Hubble law. It isn't that galaxies are moving really fast through space. It is that space itself, someone's hitting the cosmic enlarge button on the universal copier and just making it all get bigger. That's what's really going on. And so no, we're not the center of the universe. In fact, we don't think there is a center of the universe. Everybody, from everybody's vantage point, it looks like they are the center of the universe. Back to PowerPoint. So what exactly is expanding? If it's not that the universe and the galaxies are hurtling away from the Milky Way at really high speeds through space, what exactly is expanding? Well, this little animation, I think, does a decent job of explaining it. Let's go to this animation. Here it is. So there's two, when most people think, hey, the Big Bang, which is really what we're talking about. We're talking about a time in the universe's past when all those galaxies were very close together. They think of an explosion that happens in space and galaxies go hurtling through the universe. That's not, so that's this explanation for the Hubble law. That is not what is happening. Let's do the simulation 2. What is happening? It's simply that all those galaxies are staying fixed or relatively fixed on their particular grid point, but the grid point itself is just getting bigger and bigger and bigger. And so that's a huge difference. In one, all the matter, all the universe was empty except for one point, and then at t equals 0, everything starts expanding. That's not what we think happens. At t equals 0, the universe is full of galaxies, but it's much smaller in the sense that any scale difference between these two galaxies is much smaller. And as you play time forward, they just get further and further apart. The scales themselves get bigger, but galaxies themselves don't move through space on the scale very fast at all. Great. So the expansion rate appears to be the same everywhere in space, and the universe has no center and no edge as far as we can tell. How do you picture this? This is really difficult to sort of conceptualize, but here is one decent way to do it. Now again, this is going to be, our universe is a three-dimensional thing, but our brains can't handle, again, things being curved on a three-dimensional scale. But let's imagine a two-dimensional universe, similar to what we imagined when we did our black hole talk. In this two-dimensional universe, let's say we're a three-dimensional being looking down on this two-dimensional universe. You've got, let's say, the surface of a balloon. Now, this is a curved three-dimensional surface. In fact, one that curves back on itself. But in this analogy, you could imagine the universe itself being the surface of this balloon. So it's possible that this is, in fact, the true shape of the universe. In fact, if you're a two-dimensional ant on this balloon and you start moving in one direction, this balloon has no center, the surface of the balloon has no center, and it has no edge. A two-dimensional ant on the surface of this balloon could go walk in one direction and simply come back to where that ant started from. And it's possible we live in a universe that's very similar to that, where if we got on a spaceship and went off forever in one direction, we would eventually come back to where we started from in some three-dimensional shape. But I digress. It's also possible that the universe is just an infinitely flat sheet of rubber. It's also possible, we'll talk about the shape of the universe later. I don't want to get into too much of that now. Let's assume, though, that the universe is two-dimensional and think about this balloon analogy, because I think it works pretty well. Let's go back to our animation and see how this thing actually goes. Here it is. So I am going to now press play on this button, the play button, and it is going to simply inflate this balloon. And you've got 4 galaxies, A, B, C, and D, that are affixed to the surface of this balloon. From the galaxies, each of galaxies A, B, C, and D's perspective, they are not moving with respect to this balloon. They are all stationary. They are all staying put. But as the balloon expands and stretches, all of them seem to get further apart. A is getting further apart from B. There's more balloon space between A and B. There's more balloon space between B and C. There's more balloon space between C and D. Let's rewind this and play it again. And I want you to think about the Hubble law. I want you to think about the relative distances between A and B, A and C, and A and D. The same amount of space is being added between all of these, but from A's perspective, B is moving away from it at some velocity. In other words, the space between it's getting bigger. There's twice as much space between A and C, and so that space is expanding twice as much. There's 3 times as much between A and D, and so that is expanding even more. And so the further away these galaxies are from galaxy A, the faster they seem to be moving. You get the Hubble law just by taking a balloon, pasting some things to it, and inflating it. And this is what we think is really happening. It's not that these balloons, these galaxies are moving on the balloon. It's that these galaxies are fixed to the balloon and the balloon itself is expanding. That's what we say. The universe is expanding. It's not that the galaxies are just moving through space. It's that the balloon itself is getting bigger. And that's a very important distinction. Okay, so let's go back and think about radial velocities and these z factors again, and think about some fundamental limits that I had told you about in the universe and think about how that happens in the context of what we're talking about. So let's take a radial velocity of a galaxy at z equals 8.6. This is an extremely far distant galaxy. This is near the edge of the visible universe. This is one of the farthest ones we even know about. We could take a smaller number if we wanted to, but in fact, let's take it. Why did I choose 8.6? That's a silly number. Let's do a simpler value. Let's choose z equals 5. Why not? That seems more reasonable, doesn't it? All right, let's go to the whiteboard. And let's say z equals 5. Our formula is, that doesn't look like a very good 5, there you go. Our formula is VR radial velocity equals z times c, right? So for a galaxy with z equals 5, the radial velocity, there isn't much to calculate here. It's 5 times c. It's 5 times the speed of light. We could put a number with that if we wanted to, but it doesn't even really matter what that number is. It's 5 times the speed of light. I've told you several times in this class that nothing can go faster than the speed of light. How is it possible this entire galaxy can get going not just faster than the speed of light, but 5 times faster than the speed of light? Well, again, it's not that this galaxy is moving through the universe at 5 times the speed of light. It's simply that the universe is stretching between us and this very distant galaxy enough to make it look like it's moving 5 times faster than the speed of light. So objects can be moving away from each other at 5 times the speed of light. They just can't be moving through the universe or through space at faster than the speed of light. And that's not what's happening here. This isn't a true radial velocity at all. This is like a stretching constant, a stretching scale factor. It looks like a radial velocity. It behaves like a radial velocity, but it's not really a radial velocity. It's just the space in between us expanding. Okay. So if galaxies are not really moving through space at high velocities, what causes their spectra to become redshifted? Why do they seem, again, seem like we're fairly close to at rest relative to some cosmic universal resting frame. Why is it that distant galaxies appear to be so redshifted? It's not really that we're moving through space. It's that space itself is expanding between us. Well, we can also understand that with an animation. Basically what happens is as these photons, as these light particles travel through space, you know, they have a wavelength, and that wavelength, as the universe stretches under them, stretches the wave. And the wavelength will get longer. The longer this photon travels through the universe, the more space gets stretched underneath it, the longer that wavelength actually gets. Let's go and look at the animation. We've got one more to look at. Here is, again, the balloon, and you've got some photon, a blue photon traveling through it. If this photon travels through the universe long enough, the universe stretches underneath it. Again, relative to one of these grid points, the same number of wavelengths are always there, but the grid points themselves are getting further apart. And so the wavelength, as measured by somebody who is not expanding with the universe, will in fact seem to be longer. The longer this photon travels through the universe in distance and in time, the larger the redshift will get. And this is why it can get shifted past what seems to be the speed of light, because it's not really, and nothing's actually moving that fast. It's just the wavelength getting shifted underneath it. Okay, I've got one more video today. I will come back and we'll talk about a scale factor of the universe and do some examples of scale factors in the next video. So stay tuned.